Tim Kimmet, and I own the platform and systems team. And what we're responsible for doing is providing a lot of the platforms from which our applications run, and a lot of technology on top of the system. So we're a little bit closer to the operating system, not quite up in the application space. But what I'm going to talk about today are about graphs. And graphs are a very critical data structure. I've used them in several places. One of my passions in computer science was actually around graphs. I have a minor in mathematics, and I like algorithms. Algorithms are fun for me. And so I'm going to talk a little bit about them today. I'm going to talk about a very realistic use case that we use at Walmart to go and deploy our applications. So some of the more common places that we see graphs are compilers. How many people know Java? How many people code in Java every day? Yeah, so I can tell you I've got friends. You can spell it. That's a good start. It's not the coffee version. It's the but in Java, there's DAGs all over the place. DAGs are directed acyclic graphs. They're used for dependency management. They're used to calculate the order in which things are compiled. They are used for calculating circular dependencies and things like that. So if you guys know Java, you probably also know Maven, which is a very common build system. And if you use Maven for your build system, then you'll see that underneath the covers in Maven, there's a lot of graph theory in there as well. Orchestration engines are another really key component, in computer science all over the place, and there's DAGs in there as well. So, but what I'm going to talk about is how we use them in Walmart Labs, and they are the foundation for our orchestration engine that we have, and I'll talk about that in a minute. I'm going to give you some details of the design and show you how it works. We also use them in our backend infrastructure. Since I'm the platform guy, the systems guy, I worry about things like uptime and availability. I worry about service level agreements. I worry about event correlation, and we worry about root cause analysis, and we also worry about security. So what I'm going to show you here is this is a rack design. It's not really the design, but it's how we lay out our systems in our back ends. And so what I'm showing here is a couple of data centers. These are the big blocks. There's data center A and B. And I'm showing some of the racks inside of the data center. So there's rack 1 and 2 in data center A, and rack 3 and 4 in data center B. And if you look at these yellow spots, those are nodes. They're compute nodes. And the way that we have these nodes set up is that we have these complex algorithms that are called resource allocation algorithms. And what they do is, who in here builds systems? I know back there's one. You probably know about fault domains, right? You know about power grids. You know about network design and things like that. The way that these systems are laid out here, and some of the practices that I put in place, is how can we lay nodes out in a system so that we have maximum availability, right? So in this case, you see there are 6 nodes. This forms this thing called a cluster. It's just really a grouping of nodes. And these nodes might serve a small website because there's only 6 of them. Anybody want to guess some of the reasons why we spread them out this way? Brainstorm a little bit here. So yeah, you want to spread them out among racks, because a rack is one of our fault domains. So if one rack goes down, guess what? There's going to be nodes and 3 other racks in there, right? We want multi-data center because for disaster recovery, most likely this data center A is somewhere like near San Jose or in some city. Data center B would be somewhere in Colorado. So the distance far apart is so far apart that if I have a disaster in San Jose, I've still got Colorado up or somewhere else. And so wouldn't it be nice if we also designed our software deployment system so that it had a little bit of knowledge about the data center and the way we place things out, so that it can deploy software in a way so that there's maximum availability in there. So this is our software upgrade system. This is is how we do it. This is an algorithm that we use to do a rolling upgrade with 0 downtime. And so in the back end, when we lay down our systems, we know where they're at, but when we do our resource allocation and we lay down those, those 6 nodes I was just talking about, our software deployment system knows how to lay those out and how to calculate the upgrade system so that we have maximum availability. So there's a couple things about this algorithm. In this case, since there's 6 nodes, when we deploy a set of nodes, we can calculate how many we want out of traffic at any given time. So this time we chose to have a maximum of 2 nodes out of traffic at any given time. And so the first part of the algorithm is, let's go figure out how many nodes there are, and that's the size of our upgrade group. And so we've got multiple upgrade groups. In this case, there's 3, but it's a function of how many nodes there are and how many nodes I want out of traffic at any given time, right? And so after we calculate the number of nodes, we need to calculate which nodes go in which upgrade group. And the important about that is maximizing uptime while maximizing also availability. So in this case, we're going to choose nodes that aren't in the same data center and nodes that are not in the same rack, if we can get away with it. If we've got a big cluster with a lot of nodes, then sometimes it's very difficult to have nodes that aren't in the same data center or aren't in the same rack. So in this case, if you look at this first upgrade group, this green box here, you'll see that the first set of nodes chosen are nodes 2 and 5. So they're in data center A in rack 2 and data center B in rack 3. And so each one of these upgrade groups are calculated in a way so that they maintain the maximum upgrade. Or they maintain the maximum availability during an upgrade. So the way that these groups work, and this is, by the way, the same design that some of the public cloud systems work. They do calculate upgrade groups, but they don't calculate as much uptime during their actual upgrades. So we actually do a better job in a lot of them. So the way that this works is it's really walking the upgrade groups. So we walk the first one at the bottom of this graph, and this is where the graph comes in. But we walk the first one, and we do this upgrade group first. It means that we can do all the nodes in this upgrade in parallel. And when we're done, we can walk up to the parent node, and that's the group node. And so what happens in the group node is validation. So we upgrade these nodes, and it could be a software upgrade, it could be an operating system upgrade, whatever upgrade type it is. And then we walk up to the parent node, we validate it. If everything validates, then this group is done. We put it back into traffic, and we go to the next group. So during this upgrade, everything is in traffic. That's the 0 downtime part. Since we've chosen the nodes correctly, we're maintaining a maximum availability so that if one of the data centers goes down or we lose power in a rack, that we assure that we've got nodes spread around correctly. So how do we produce a system that has the ability to walk these nodes intelligently and to have different algorithms among them? And this is where the graph comes in. And so this is a directed acyclic graph. There's many different kinds of graphs. How many of you know what GraphViz is and some of those graph tools? Have you used those? Yeah. So GraphViz, if you've never used it, go download it and take a look, because it's all about this kind of stuff. It can do many different graph types. It's a very good visual tool. I use it all the time for debugging purposes. And this actual graph here is produced by a plugin that I wrote in Eclipse, and I'll show you that in a minute. But this DAG, the directed part are the arrows. They always point in a certain direction, which means that you can't go, you only go in one direction while you traverse through the graph. And the acyclic part means that we've got no cycles. So the reason why this is used in some of the compiler technology or other things, you don't want 2 pieces of code pointing back to each other, because which one do you compile first, right? So these are some of the things that, some of the rules in the DAG. So the reason why we chose this actual data type for our software deployment system is because we want to use the traversal algorithms, and we want to know when we can do something in parallel. And so the way that we walk the graph, if I go back to this little algorithm here, is we start with the leaf nodes. because the leaf nodes have no dependencies on them, right? Which means we can operate on those in parallel because they've got no dependencies. So in our system, actually, we could have hundreds of these, hundreds of things we can do in parallel at once. And in order to make it extremely efficient, we can actually spread these hundreds of nodes across hundreds of machines if we wanted to, and execute them all in a different process space, because we can have a central caching system that knows how to bring them back together, manage the state, see where it's at in the graph, traverse it a little bit further, and spread it out again. So if we wanted to do something big, we can do that with this data type as well. So that whole system I just described is actually a part of the algorithm that a lot of these big workflow engines use to become really efficient in the execution of the workflow. So I'm going to show a little bit of code, because Rupa said if I didn't show code, she'd get really angry with me. So, so I have some code to show you. And this is some code that we have for our directed acyclic graph. And it's a pretty well abstracted out data type. Here's the actual class body here. I don't know if, can you guys see that in the back?
Sort of.
Probably barely see it. So, so this is the first part of this code, which is on the left-hand side, is really the construction of the graph. And if you look at some of the graphic or the graph algorithms out there, it's really interesting why there's no DAG actually in the Java runtime. Doug Lee created a bunch of the thread pool and a bunch of those APIs, but they never created graphs. And graphs are used all over the place. So we write them all over again. It's pretty funny. But in this case, the way that this graph is just a map of the nodes, the node names. But in this case, it's node E, so it's any object you want to throw in there. And so it's a node to a set of its adjacent nodes. So in this case, if you look down here to this little structure, we've got a node A, and that node A points to node B and C, right? So in the code, in this code right above it, you can see on line 7 to 9, I construct the nodes. And since this graph is pretty opaque, I can construct any kind of object and throw it in there. And I construct the DAG next, that's on line 11. And then I start adding nodes to the DAG. So I add all the nodes, A, B, and C. Now if I were to print this graph right now, what do you think would happen if I just printed it right after line 13? It wouldn't really be a graph, would it? It would just be a bunch of nodes. So the next thing I do on 15 and 16 is I start connecting the edges. So that's where this data type becomes really important. And so if you can see the code on the right-hand side here, you'll see some of the more important properties of a DAG. So if you look at this bottom block down on line 69, or actually on 67, I start checking for cycles. And this is a really important attribute about the DAG, because a lot of the traversal algorithms that we use, if there's a cycle, it'll never stop traversing. Because some of these we don't keep track of nodes that were already visited for performance reasons. And so we make sure there's no cycles when we construct a graph. And so all of these are very key properties of the DAG, and that's what this data type does. So this is the actual code to stand up this whole structure on the left. And you can see it's similar boilerplate code that I had earlier. And so on lines 7 to 14, we construct all the nodes in that graph. And we create the DAG, then we add all the nodes to the DAG, and we connect all the edges. And so this is somewhat of a hard-coded system. But you can imagine that if I had my whole site, the topology of my whole site and all of my compute nodes that were back here, if I had all of these compute nodes in a configuration management database, and you tell me to go deploy your service across these 6 nodes, then the way that it works is I go query that database. I know from the database, I know which data center it is, which rack it is, and I even know on which actual physical machine it is, because these are virtual boxes, right? So I get down to the level where if there's 2 nodes on the same virtual box, then I'm not going to choose those, because if that box goes down, then those nodes can go down, right? And so the way that this works is I query a configuration management system. There's a rules framework that it runs through, spits out the nodes. We dynamically construct this graph here. But the way that the graph is constructed is in such a way that we follow those rules. And so we create the upgrade groups based on feedback that the user gives us. And once we create these upgrade groups, now we've got a system that we can throw at our orchestrator, and it can go do the code deployment. So this is the secret sauce between a lot of the way that we upgrade code in our systems. And the nice thing about this is we can do this for just about anything we want to do. So if I want to upgrade an operating system, I can do that. If I want to upgrade software on the node, I can do that. If I want to go and do a configuration management change, I can do that. And guess what? I know that it's all reliable because we've tested these systems really well. And I know how to debug it because it's the same algorithm every time. So it's beautiful. So I'm going to give you a little demo now of some of this stuff. So this is my DAG. You guys in the back probably can't see it really well, but just to show you, it's actually running code. It's in Eclipse, and this is actually a plugin that is sitting here. The actual plugin code is sitting over here. And this uses a library in Eclipse called Geth. And Geth is it's basically a graphical piece in Eclipse that a lot of the things you actually see in Eclipse are in Geth. But it has some of these basic libraries for doing things like drawing a node. It doesn't really draw a graph, but it draws the node. And they do have some graphic-based libraries. So if you want to poke around and learn about graphs, it's a good way to do it. You can do some plug-in programming and learn how to do it. So what I did is, these are all nodes. These follow, this is basically the same construction that I have in that graph earlier. And what I'm going to do is just show you this traversal algorithm. So what I do is I can right-click here, and I'm going to say traverse this graph.